So that motivates the continuous state space linear Gaussian Markov model. As with the hidden Markov model discussed in the previous lecture, all we're given is the observation sequence x1 through xt, where each observation is in RD. And now the goal is to learn the underlying state sequence S1 through ST. So similar to the HMM, we want to learn what's going on with this hidden state sequence. Unlike the HMM, the only thing we're learning is this underlying state sequence. We're not learning the emission distributions called B last time, or the transition matrix A, because we now have a continuous transition distribution. So for this model, again, all distributions are Gaussian. So here's another way of writing the generative process we discussed previously. The distribution on the state at time t plus 1 given the state at time t is a multivariate Gaussian with mean equal to c times st and covariance q. So we're assuming that q and c are known or can be estimated in advance. And then the distribution on the observed sequence, xt, the observation at time t, given the underlying state at time t, is also a multivariate Gaussian with mean equal to d times the underlying state st and covariance equal to v. And again, we're assuming d and v are either known or can be estimated. So for the previous problem that we discussed, c and d were known from the physics of the problem, and q and v were estimated somehow in advance. So notice that, again, with the HMM, with the discrete HMM, we had these other model variables, pi, a, and b, and we wanted to learn those as well. Here, we don't have any of those. All we want to learn is the underlying state vector as a function of time. So again, just to emphasize, let's notice how this is very different from the discrete HMM. With the discrete HMM, we wanted to learn pi, a, and b, where pi was an initial state distribution, where we had a discrete set of states. A was a transition matrix among the discrete set of states, and then b contained the state-dependent probability distributions. In the linear Gaussian Markov model, the situation is different because we don't have to learn b, because since each state is going to be unique, because the state is in a continuous space with a continuous transition distribution, the distribution on each x is also going to be different. The way that we constrain it is by letting the distribution family be parameterized by s in this way. However, because st is continuous valued and unique, this distribution, the parameters are going to be unique for every value of x. Also, we don't have the matrix A to learn because we don't have a discrete set of states. Again, S is a continuous valued random vector with a continuous distribution, meaning that every state at every time point is going to be something brand new, a new continuous valued random vector. However, it's constrained by this distribution, which is what is going to make the problem of learning the underlying state possible. What we can learn in this case are these two posterior distributions, and for the rest of the lecture we're going to be interested in the first one. But we can learn the posterior distribution of the state at time t given the sequence that we've observed up until time t. So this is a distribution on the current state given all of the data I've seen up until that time. We also might want to be interested in learning the posterior distribution of the state at time t given all of the data, including future data. So this would not be a real-time model. The first problem has a name. It's called Kalman filtering. It's what we'll focus on today. It's learning the continuously evolving distributions on the states as in a real-time setting. The second problem is known as Kalman smoothing. It requires one extra step that we won't discuss. It's similar to the backward algorithm for the hidden Markov model. This would be something where we have all the data in advance and we want to then do some sort of a post-processing. So the first problem has to do with tracking objects, and that's what we're going to focus on for the rest of the lecture.